Alright, welcome to Floyd's algorithm. So to be completely fair, in the real world it's called the Floyd-Warshall algorithm, and there's also a guy called Bernard Roy who kind of invented it himself as well, but decision's just going with the Floyd algorithm. This is a long, thorough algorithm, I would say. It's not necessarily very complicated, you're just comparing two numbers and seeing if they're bigger, but it's a long one to explain. And it's got some steps that maybe don't make too much sense until you get to the end. So we're going to go straight into it. The point of this algorithm is to find the shortest distance between every vertex. So Dijkstra just found you the shortest distance between A and D. This will tell you everything, A and D, A and C, B and C, and so on. But to do this, we have this sort of set of tables that we need to maintain. We've got distance tables and we've got root tables. And we're going to have, in this example, our distance tables are at the top, are on the left rather, and our root tables, which I can't write apparently, are on the right. Distance tables should be read as from these numbers on this side. So if I was talking about this point here, that would be from B to D. Okay? So let's go through the steps. Step 1, complete an initial distance table using infinity if there is no direct route between the vertices. So first off, we can put zeros or blanks in A to A, B to B, C to C, and D to D because they're obviously not connected. They obviously are immediately connected to each other. And then let's go through. So for B, it's got a root of 4 to B. For A, it's got a root of 7 to C. And there is no direct connection from A to D because it's a one-way street, so we put an infinity in there. For B, it's got direct connections to A and to D, but not to C. C only has a direct connection to A, and D has a direct connection to A and B, but not C. Now for the root one, so that's our step 1, complete an initial root table. We just repeat the top row. So the top row says A, B, C, D. That's literally all we're going to write for now. And the root table, as far as like what it's doing, won't make any sense until the very end. So don't worry about it. Just keep updating it. Now we're going to do what I call the A iteration. I think they call it first, second, third, but I think it's easier to think about it in terms of the letter. And the way this goes is we start off by highlighting the first column and row. I'm actually going to just sort of box them off because the highlighting capacity of PowerPoint is not great, and also this is fine. And copy them out, leaving those values unchanged. So we've got our new distance and root table, and everything that's inside that column and row, that A column and row, is going to stay the same. So it's going to go 0, 4, 7, infinity, and 4, 7, 1. And this one is going to go A, B, C, D, A, A, A. So, done that. That wasn't too hard. And now the tricky bit. Consider each unshaded position of the distance table in turn. If the sum of the corresponding row and column in the shaded part is less than the value, replace it with the sum and update the root table with A in that position. So, let's take this one as an example here. So what we're saying is we're going to compare the sum of these two values in the shaded column and row. So that's 1 and 4. We're going to add those two together, which gives you 5, and we're going to compare that to the number that was already there, which is 9. Now 5 is less than 9. May surprise you. So we're going to update that value. We're going to write in a 5 there. And we're going to also update the root table with an A in that position. And that's all it is. You've got to do that with all of the unshaded squares. Now some of them are definitely not going to change. These are value 0, so they're not going to be, you're not going to find any distance which is less than 0, so that'll stay the same. Let's go through the rest. So for this one here, there's an infinity in that box to start with. We're comparing it to 7 plus 1, and 8 is definitely less than infinity. So we'll update it, and we'll put an A there. What about this one here? 7 plus 4 is 11. That is definitely less than infinity. Okay, B to C, Yep, we've got another 11 we can update there. I shouldn't be writing 11 there, I should be writing A. We can update that one as well. And then here's an example of one we can't update. So we currently got a 9 in this box, and we're comparing it to 4 plus infinity. Now infinity is still more than 9, so that will stay the same. The letter will stay the same, we don't update it. I've decided to do the things I'm changing in green and the things I'm not changing in red. You would normally want to show this by circling the thing that you are changing, just so it's obvious what you're doing. And this value here, we're comparing infinity to infinity, so it's not going to change. You could change it, but it doesn't make any difference to your final value, and it's just going to be more complicated. So there we go, that's our updated table. That's the A iteration. And then 5 says to repeat step 3 and 4 with B, C, D, etc. until we've done the iteration for every letter. So we're going to do 3 more iterations, 1 for B, 1 for C, and 1 for D, and then we'll be more or less done. So let's go through the process a bit quicker this time. For B, shade in the corresponding row and column, so it's the B one this time. Copy that column down from the iteration above, so we're not copying it from the original values, we're copying it from the values we found. And obviously don't forget we need to copy out the root table there as well. And then we're going to compare our values. So I'll start with the top left. In fact, the diagonal is always going to stay the same, isn't it? Because they're all zeros, so we don't need to start with the top left. Let's keep going along the A row. So we are comparing in this row. We're comparing 15 to 7. 15 is definitely bigger than 7, so it won't change. Then we're comparing 13 to infinity, and 13 is smaller than infinity, so that will change. And I'm going to update the label. Now, remember on the previous one we updated the labels to be A's because it was the A iteration. Here we're on the B iteration, so we're going to update them to B. We look at the C row, 15 compared to 7, not going to change. And infinity compared to 16 is going to change, so we can update this one to 16. Oh no, sorry. Yeah, 16. No, 20. 9 plus 11. I knew there was something wrong there. There we go. For the D and A one, we're comparing 9 to 1. That's not going to change. And for the next one, we're going to compare 16 to 8, and that's not going to change either. So we only updated 2 values this time, and you will find that the number of things you update doesn't change, doesn't increase that much as you go through it. So we want to copy the values that are in the things we haven't changed and update the values on the ones we have changed. So yeah, there we go. Okay, do the same thing for C. Let's do this a little bit quicker again. And the hope is basically you get into a sort of rhythm with it. So this will stay exactly the same. And so will this. And then we'll need to update our values. So we know the diagonal is going to stay the same. And then we need to compare. So let's start from the top left. We're comparing 4 to 18. That's not going to change. 13 compared to 27. That's not going to change. 4 compared to 18. That's not going to change. 9 compared to 31, that's not going to change. 1 compared to anything is not going to change. 5 compared to 19 is not going to change, and we are done. So in this case, in this iteration, nothing changed. But you still got to do it. You still got to do 1 for every single value. Okay, let's finish off with the D column and row. Let's do set 3 first, so fill in the same values from the one above. Fill in the root for that one above as well. Do the diagonals unchanged. And then starting from top left, 4 compared to 18, 7 compared to 21, 4 compared to 10, 11 compared to 17, 7 compared to 21, 11 compared to 25. So yeah, again, no values updated. And this is the point where we stop. So we stop because we have used all 4 iterations. We've done an A, B, C, D. And we consider the second thing, which is, well, what the hell have we just found out? So the question that sort of goes with this is to find the route from C to D. I'll find the shortest route from C to D. So how do we do this? Well, first thing we do, we use the distance table. And we read across, remember this is the from part, we read from C to D, and that's going to give us that the minimum value, the length of that is 20. Okay, but what actually was that route? So I came up with a way of sort of showing this as to how I want to get what I want to get. So I know I wanted to go from C to D. So I'm now going to use the route table, and I'm going to look up from C to D. And if I look that up, it gives me the value B. So that means that the quickest route from C to D is not straight from C to D. I mean, you can see on the map that's not possible, but that we have to go to B before we go to D. So we'd write that in. And then we'd look now on the C row still. We want to say, well, what's the shortest route from C to B? Well, according to our our route table, that gives us the value A. Okay, so we have to go via A. So we say, okay, what's the shortest route from C to A? And that does have the value A. And that is where you stop. You stop when this value here corresponds with this value here. And the actual route that you want to take can be read off in this sort of fashion. So our shortest possible route is C, A, B, D. And we can look at the original diagram. We can say, well, C to A was 7, A to B was 4, and B to D was 9. And that, yeah, that adds up to 20. So yeah. So that's Floyd's algorithm. Hope you enjoyed that. We're going to look at one more example. So here it is. They're unlikely to give you an 8 input table and say, please do all of this at once. It's very important. They're more likely to say, we've done most of the iterations, or we've done, in this case, 7 iterations. You need to do the 8th. So let's just go through that process, and we want to find the minimum route and what actual vertices we pass through to go from D to F. So we are doing the 8th iteration, which means we are highlighting the 8th row, which is this is the H iteration, is how I would probably call it. And then we need to go through the process. So obviously this is going to stay the same. And the corresponding values down here will stay the same as well. There's a lot of E there, isn't there? Okay, so we know the diagonals are unchanged. And we know they spell out like A, B, C, D, E, F, G, H anyway. Okay, so starting from the top, I'm afraid this is going to take a little bit of time. So we compare 8 to 2, we compare 11 to 5, we compare 5 to 7. Okay, that is going to update. We compare 9 to 3, 11 to 11, not going to update that. And 9 to 9. I'm not going to update that. Okay, let's look at the B row. We're going to compare 12 to 6, 17 to 3, 11 to 5, 15 to 9, 17 to 9, and 15 to 7. So nothing much has changed yet. On the C row, 9 to 3, 11 to 5, 8 to 2, 12 to 6, 14 to 6, and 12 to 4. On the D row, 7 to 1, 9 to 3, should have written 1 in there, 9 to 3, 12 to 6, 10 to 4, 12 to 12, and 10 to 10. So far, not much fun's happened. E row all has infinities on it, so all of these are going to be updated. So we'll put in 3, 5, 8, 2, 8, and 6. Cool. F row, so we're going to have 5 to 7. That is going to change. 7 to 1. 10 to 4. 4 to 6. I should be leaving those in red, shouldn't I? Because I'm not changing them. So 4 to 6. 4 is going to update there. 7 to 2. And 8 to 8. And then on the bottom row, we're comparing 7 to 2. 7 to 9 rather, sorry. So we will update that one. 8 to 3. 12 to 6. 6 to 8, so that is going to update. 10 to 4. And 12 to 2. Phew. Okay, so we changed some of our values, and because this is the H iteration, we're going to write a H in each of those values that we changed. Cool. And then all of the other values are going to stay exactly the same. So you can see here, it's not a terrible algorithm. Like it's obviously very useful and powerful as well, but it is a bit tedious to work through, and you've just got to make sure that you don't make any mistakes and that you're constantly checking what you're doing. You can see even on that process there, although I was just comparing two numbers, I occasionally would put the wrong thing in the wrong place, and I had to be checking as I did it. I'm not going to pretend I'm perfect at this algorithm just yet. Okay. So minimum time and route from D to F. So remember, for our minimum time and distance, we want to go from D, which means from D to F, and that gives us the value of 12. And then how do we get there? Well, we need to do that whole process where we start with D and we go to F and we look it up on the distance table, and that tells us G. So it means we're going to need to go via G. So we look up D to G, and that tells us C. So we look up D to C, and that tells us B. So we look up D to B, and that tells us A. So we look up D to A, and that tells us A, and we can finally stop. So our actual list of things that we're going to go is, remember, along and across would be D, A, B, C, G, and F. There you go. Floyd's algorithm, boys.